Hello everyone, it's my great honor to introduce our work here. Barre, empowering simplified and versatile programmable congestion control in high-speed AI clusters. My name is Yajuan Peng. I'm from Fudan University, and this work is accomplished with Haoran Wei and his colleagues from ByteDance. We will offer some insights on deploying congestion control solutions in data center. First, I will provide the background of our work. We have observed that modern high-performance and AI data centers are still employing DCQCN as the congestion control solution. However, DCQCN was proposed 10 years ago, and during this period, the network hardware and workload have undergone significant changes. Our investigation indicates that state-of-the-art congestion control algorithms are currently facing a dilemma, as the deployment requirements and the cost of these algorithms do not match the capabilities of current commercial NICs and switches. This issue leads to the challenges of large-scale deployment in production. The second observation is that large-scale distributed AI tasks introduce multi-dimensional and stringent performance requirements, which are different from traditional cloud workloads. For instance, this table lists the characteristics and performance requirements of some collective communication operators. Due to the differences of incast scale and key requirements, it is difficult to establish universally optimal parameter settings for a whole AI task. And furthermore, the transitions between different traffic patterns can frequently trigger severe congestion. Based on above observations, we believe that high-speed data centers require a practical congestion control solution, which needs to comprehensively consider the high cost of hardware, scalability of cluster, and the emerging performance requirements. Therefore, we draw on the classical saying of the hardware lottery to put forward three fundamental requirements for the design of congestion control algorithms as broad applicability, simplified logic, and implementation practicality. We discuss the design options by analyzing the characteristics of RDMA hardware and the RoCE V2 protocol to achieve coordination of hardware, software, and algorithm. First is the congestion signal. ECN, as the most widely adopted and supported signal, is simple and effective. NT is precise, but password requires special switches support, which leads to deployment challenges. RTT can provide end-to-end network latency, but is sensitive to path stability, especially in multi-layer span-leaf topology, which is difficult to determine a baseline value. The second one is the rate control mechanism. Credit-based control offers high performance and is used in InfiniBand solutions, but it is expensive and requires modification of the RoCE V2 protocol. The window-based control achieves perfect precision, but it is incompatible with RDMA and RNIC, and is tightly coupled with the transport protocol stack. Rate-based control is deployment-friendly and widely supported by NICs, but it is unable to limit the number of paths in flat. Therefore, we need to co-design the algorithm based on the hardware functions, while also reducing the inherent limitations of the hardware. The Programmable Congestion Control (PCC) provided by SmartNIC offers an interface for custom algorithms. As an emerging low-cost solution, it only supports rate-based control and lacks the congestion window, Therefore, in large-scale, high-speed networks, it is challenging to utilize limited computing resources to handle such large amount of traffic events. On the other hand, RoCE v2 lacks perfect ACKs, so many algorithms use per unit time CNP reception to adjust the rates. However, this fails when the transmission rate is extremely low, where the product of RTT and the sending rate is less than 1 MTU. The figure illustrates the case. We are using RTT-based rate increase intervals. Low sending rate will cause packet interval to exceed 1 RTT. So CNP intervals do too. Here, even with each packet triggering a CNP, rate keeps increasing. This leads to wrong rate increase during slowdown at very low sending rate. Based on above analysis of the hardware and the protocol stack of the data center network, we conclude that Ethernet congestion signal and rate-based control are more in line with the current infrastructure of the data center. So Barre employs the two options and makes full use of the capabilities of the NICs to mitigate the impact of inherent limitations. Our basic idea is to utilize the RTT prot packets carried by the NIC and the high-frequency CNP signals to implement an adaptive interval adjusting AMD algorithm. When the RTT prop packet returns to the sender and no CNP is received, the rate increase is triggered. As the modern NICs are able to respond to CNP within 1 microsecond, we make the algorithm perform a rate decrease for each received CNP signal and make the reduction smaller in the meanwhile. Barre can automatically adjust the interval of increase and decrease based on the network conditions, and thereby achieve rapid convergence, stability, and fairness. To address the challenges brought by RDMA NIC and RoCE v2 protocol, we designed 3 functional components for Barre. The first one is fast increase. The classic AMD algorithm uses a fixed increase factor alpha, which makes it difficult for the algorithm to determine a universal optimal setting across different traffic patterns. Although some works have proposed dynamic alpha, but most are complex to implement. So we proposed a simple solution. We set a conservative factor alpha and an aggressive factor A in the meanwhile. When the sender has undergone multiple rounds of rate increase and has not received any CNP signals, it indicates that there may be a relatively large amount of idle bandwidth in the link. In the next turn, the factor changes to the aggressive value A. Once the CNP signal arrived, the factor is restored to alpha. The experimental result shows that fast increase achieves excellent performance in both mass flow and elephant flow. Dual-lock is designed to address the issue of wrong rate increase, introduced by RoCE and ACN. When the CNP signal is sufficient to reflect the congestion state, we use the logical AND relationship between timer and bed counter to limit the conditions for rate increase, so that the rate increase interval of high-speed flow is equal to the real-time RTT, where the rate increase of low-speed flow is controlled by the counter. The result shows that dual-lock can reduce the switch queue length by up to 19% under large-scale incast. Due to the lack of perfect ACK, and the packet header that carries the payload size in UNIC. Algorithms cannot achieve precise control over the inflat path like congestion window do. So we designed the inflat monitor. The TX events generated by PCC provide the amount of reported transmission data. We can calculate the accumulated sending batch during current RTT. Once the accumulated value exceeds the theoretical maximum value, the transmission rate will temporarily be set to 1/4 of its original value, and keeps until the CMP signal reaches the sender. The result shows that inflat monitor effectively improved the overall throughput and the large-scale congestion. Our algorithm is implemented on Bluefield 3 SuperNICs and fully leveraging the capabilities of PCC. This figure illustrates bar system architecture and the control flow. During the implementation, we discovered some problems in using real-time RTT as the dynamic interval for rate increase, and designed RTT-based enhancement to address the challenge. Due to the hardware limitation, the loss rate of the RTT probe packets may reach as high as 8.9%, resulting in error in calculating the real-time RTT. We modified the RTT response packet to both carry the sending timestamp of the RTT request packet and the arrival timestamp of RTT response packet. To ensure fairness among the flows of different path lengths, we set different increase factors for each flow based on their RTT. And the experimental results show that RTT-based enhancement has effectively improved the overall throughput in both the test environment and the real training tasks. Next, we evaluate Barre with the comparison between DCQC and InfiniBand IB. These two are respectively regarded as the most commonly used large-scale deployment solution and the performance ceiling solution. And here are our experiment settings. As O2O communication is currently the network bottleneck in large-scale MOE model training tasks, we evaluate Barre through Nico O2O test. As the transmission message size increased step by step, we record the average latency and throughput of the three solutions separately. The result shows that Barre achieves superior latency and throughput comparable to IB, as Barre is deployed on commercial NICs with lower hardware and deployment cost. And also, DCQC has failed to converge to the optimal parameter settings. So its performance has experienced significant fluctuations. Currently, Barre has been deployed on our RoCE clusters within 30,000 GPUs for over a year and has achieved an average overall improvement of 10% in end-to-end benefits for training tasks. This figure is taken from the production switches. It demonstrates that Barre has outstanding performance. Based on Barre's techniques and the current capabilities of the hardware, we optimize some parameters of DCQC, especially the dynamic rate increase based on RTT, and the high frequency rate decrease based on CMP. The nickel ore-reduced experiment shows that after optimization, the normalized throughput is increased by an average of 19%. Additionally, we conduct tests on a cluster of 4 clients and 1 server. The left and the right figures are the default and optimized results of this execution, respectively. The results show that the stability, fairness, and convergency of the system have been significantly improved. All these results once again support our viewpoint that the design of algorithms should take into account both the characteristics of software and hardware. And it also indicates that Barre's ideas can be used to assist in the optimization of other congestion control algorithms. In summary, we proposed a congestion control solution for high-speed AI data centers. Instead of fantastic, Barre is designed to be practical, scalable, simple, and easy to deploy, while also achieves outstanding performance. We hope that our idea can provide more people with useful assistance. Thank you for your attention. We welcome your communication. Please feel free to contact us via the email